Okay, so the Schottky barrier diode is based on the concept of metal semiconductor junction. Okay, so we have seen metal semiconductor field effect transistor MESFET in the beginning of this unit. And in that, we have told that there are two types of metal semiconductor junctions possible. One is the conventional metal semiconductor junction, and the second one is going to be ohmic contact. So here, this diode is going to work on the principle of ohmic contact only. So the metal contact has to be ohmic, and no PN junction has to be formed between the metal and the silicon layers. So you see, you have a metal layer, you have a semiconductor layer, and when you are going to join these two, it is going to form an ohmic contact. So you are going to have a separate N plus diffusion region for generating ohmic contact. N region is heavily doped with electrons as majority carriers, and N plus is a very heavily doped region. Okay, so I am going to use aluminum as the metal. So I am going to deposit aluminum directly on silicon. So a metal semiconductor junction is very easily formed. So if you are going to fabricate a diode using this concept, having a metal semiconductor junction, so the characteristics of the VI graph will be exactly same as that of a PN junction with slight modification. So instead of having two semiconductor regions, I'm going to replace the P in a PN junction diode. You have two regions, P region and N region. P region will have a majority carrier to be hole. N region will have majority carrier to be electron. All these basics are known to you. If I replace the P region by a metal, then also what they say, metal semiconductor junction will also have the same characteristics, or I can say similar characteristics of PN junction diode. I cannot say it is exactly same, but the nature of the graph of VI characteristics is going to be same as that of your PN junction diode. Such a diode which is going to have a metal semiconductor junction is going to be called as a Schottky barrier diode. And the diagram and other details are given here. You can see that I'm going to take a P-type substrate. Over that, I'm going to have I'm going to grow this N-type substrate. In the N-type substrate, I'm going to diffuse a heavily doped N plus region. And that N plus region will serve as one terminal, and this N region will serve as one terminal. And above these two terminals, you are going to have aluminum contact. So here you see you have a metal semiconductor junction established, and you have an SiO2 insulating layer in the portions other than where you have this aluminum contact. So you know a diode will have a cathode and an anode. So you have two aluminum metal contact established over the device, one over the N-type region and one over the N plus type region. And N plus is a heavily doped electron region. So you can see this region, this circled portion, what you see is going to be the metal semiconductor junction, which is going to produce the required VI characteristics. And the symbol for Schottky diode is given like this. See, normal diode, the symbol is a triangle followed by a line, correct? But in Schottky diode, this line is going to be somewhat changed. So you are going to have this line like this. Some extension you are going to do to this line. Okay. So this is the symbol for Schottky barrier diode. So it's similar to PN junction diode, except that to differentiate your PN junction diode from Schottky barrier diode, I'm going to bend this line like this. That is what is given. The everything is shown here. And the contact 1 is going to be a normal contact, whereas contact 2 is a ohmic contact. Contact 1, they name it as Schottky barrier because metal and N region. And contact 2 is ohmic contact because I'm going to have metal and heavily doped semiconductor. So two contacts are shown here, right? So one is Schottky barrier contact, another one is going to be ohmic contact. So because of the contact potential between the semiconductor and the metal, it generates a barrier for flow of electrons from the, you know that whenever you are going to have a metal semiconductor junction, the electrons are going to flow from the semiconductor towards the metal. For the electrons to flow freely from semiconductor region to the metallic region, the potential barrier has to be less. But what they say is conventionally all metal semiconductor junctions will have a certain amount of potential barrier. You cannot make it completely negligible. So whenever you make a metal semiconductor junction, a potential barrier is formed. So when the junction is forward bias, you know the depletion region is going to be lowered and electron is allowed to flow freely from the semiconductor to the metal in large quantities. This is just the same as the operation of your conventional metal semiconductor junction based diodes. They always you have a whenever you have a metal semiconductor junction, electrons are going to flow from the semiconductor to the metal. And the reason, the Fermi level of semiconductor is more than the Fermi level of your metal. That is the reason why the electrons are flowing in that direction. And in forward bias, the depletion region width will be lesser. So more and more majority carriers will cross the depletion region, leading to a large quantity of current flowing inside the device. So that is going to be the conduction current in the PN junction diode. Whereas in the PN junction diode, minority carriers carry the conduction current and it occurs an appreciable time delay from on to off state. Okay, so here in conventional PN junction diode, you have what is called as drift current and diffusion current, right? So here what they say in the Schottky barrier diode, the majority carriers are going to be conducting in large numbers to produce what is called as the conduction current. Whereas in PN junction diode, they say the minority carriers carry the conduction current, whereas the majority carriers will be involved in drift and diffusion current. So here you don't have a PN junction layer, you have only a metal semiconductor layer. So you don't have the concept of drifting and diffusion. You have only one conduction current because of majority carriers. But when you compare this with conventional PN junction diode, the majority carriers will have drift and diffusion current, and the minority carriers will have the conduction current as it in, because you have a time delay when the device is going to be switched from on state to off state. The minority carriers have to be stored because the minority carriers cannot be removed immediately. So it takes some finite time for the device to turn itself from on state to off state or from off state to on state. It takes some finite time. For that matter, any device in nature requires some time to turn on. A simple example is your fan. You turn on your fan immediately does not run at maximum speed, right? It takes some time to reach the maximum speed. So every device, when it is turned from on state to off state or off state to on state, it takes a finite amount of time for it to reach the steady state. So that is what is told here. And this characteristic puts the Schottky diode an advantage because there are no minority carriers, right? So it instantly you can turn on or turn off this device when you are going to apply some potential. So that is what is shown here. See here, since there is the exhibit, since minority carriers are minimum, there is negligible storage time for the electron to flow from N type into the aluminum almost right at the contact surface. So what they are saying is, since there is no minority carriers here, so literally when you say there is no the time delay for evacuating the minority carriers from the depletion region is very, very minimum. So instantly your diode starts conducting. And one more advantage is, conventional PN junction diodes will conduct only after 0.7 volts when they are made of silicon, or 0.2 volts when they are made of germanium, right? But this Schottky barrier diode can conduct immediately after 0.4 volt. So this 0.4 volt is the forward voltage. So once your device reaches zero point 0.4 volt, the device starts conducting, or I can say the device turns to on state. So this zero point 0.4 volt can be used for clamping and detection in high frequency operation. So this 0.4 volt across the device can be used for high frequency operations like microwave and other applications. So it is just like extension of conventional PN junction diode, but only thing, instead of having a semiconductor depletion layer, we are going to have a ohmic contact based depletion layer. Okay, so the metal semiconductor surface is interface is surface. The Schottky barrier is rather than a point contact. So you have two types of contact here, right? One is Schottky barrier, another one is ohmic contact. So in general, in the ohmic contact, it's going to be a surface level contact, but in the Schottky barrier, it's going to be a point level contact. So in the diagram I told you, right, we have 1 and 2. 1 is a Schottky barrier contact. 2 is going to be the ohmic contact. So the ohmic contact is making interface with the entire N plus region. So it is a surface level contact. But this ohmic contact, Schottky barrier contact represented in terminal 1, it makes contact with the N-type region only at this point. but here it makes contact with the N plus region fully. So that's what they have said here. The metal semiconductor interface is a surface, whereas the Schottky barrier is rather than a point.